Right. So where we were, I'm trying to derive the sandwich or composite material under axial loading. So first of all, Px is equal to P1 plus P2. We're going to assume that the strain induced on both material are the same. This is because the strain is very small. And from here, we wrote up that strain 1, which is for material 1, strain 2 is for material 2, is equal to L1 minus L0 over L0. Then based on Hooke's law, we know that stress 1 is equal to E1 epsilon 1, stress 2 is equal to E2 epsilon 2. And then we rearrange the formula. And finally, we finish off where Px is equal to stress 1 A1 and stress 2 A2. Okay, so we know that note that epsilon 1 is equal to epsilon 2. Okay. So with this expression, we know that stress 1 over E1 is equal to stress 2 over E2. How many of you prefer the thicker ink? Oh, this is okay. Yes. Okay, thicker ink next, Lisa. You get thicker ink. Okay. So from here, we know that stress 1 is equal to E1 over E2 multiplied by stress 2. Stress for material number 2. Okay. So we know that Px is equal to what? Px is equal to stress 1 A1 plus by stress 2 A2. But we also know that stress for number 1 material is equal to E1 E2. E1 over E2 multiplied by what? Stress 2. So we substitute that in. So we have E1 over E2, okay, multiplied by stress 2 A1 plus by stress 2 A2. So if here we can have Px is equal to, we only have stress 2. So this will be equal to E1 over E2 A1 plus by A2. So from here, we know that stress for material number 2 is equal to Px over E1 over E2 A1 plus by A2. Okay. And likewise, if I were to derive everything again, stress 1 or stress for material 1 is equal to Px bracket A1 plus by E2 over E1 A2. Okay. So this is the formula that I will provide, okay, to determine axial load in the sandwich material. I repeat again, I will provide. Okay. Okay, let's look at the worst problem that Mother Nature can hit on us. Okay. So example. Okay, number 1. So we're going to look at this example, and this is the figure. I post this on Avenue to Learn. And this, as I said, was a question during COVID times, okay, that I gave. It was in term test number 2. Okay. That year was pretty bad. 102 students failed out of 180. I still remember. And then the final exam, I let the student take 6 hours to do it. And it was all from the homework. and a lot of people pass. Okay, I learned my lesson because they did not get into my mind. I want you to go inside my brain now. Okay. So the question asks, determine the maximum stresses in material 1 and material number 2. Okay. Now over here is a longitudinal view, and this is point A. Point A in the cross-section view is over here. Okay. So when you look at a problem like this, you have to know what formula you're going to apply. First of all, what sort of loading is this structure? Okay, so you have to determine the loading condition. Loading conditions, you have to focus on the forces. So we know over here we have a what? We have a load acting in this direction. Let me copy this. We know there's a load going in the horizontal direction. And this is our AX. And over here, we have our AY. If we were to look in the cross-sectional view, right, we have point A down here. And point A, the arrow is coming towards our face. Okay, the arrow is coming towards our face. At the cross-sectional view, we sketch our position of our neutral axis. Sorry, wrong word, centroid. We sketch our centroid. One centroid is in this direction. The other centroid is in this direction. Okay. This is our ZZ axis, and this is our YY axis. Right? So from here, how many or what are the bending moments that are linked or that you can see over here? Is it 1 or is it 2? But before we go on, we know, right? We know that with AX, loading, the structure is under eccentric condition. Right? Eccentric means what? If we look at the formula, the general formula as a whole, stress is equal, stress X is equal to Px over A plus or minus My over Iyy Z plus or minus Mz over Izzzy. Okay. We have a Px. The Px, if there is a Px, means is what? Means it's under what? Eccentric loading. Are we clear? Some student ask me, how do you know what loading condition it is? Okay, for now, we know we have what? Eccentric loading because of our what? Axial load, which is the Px. Then the next we ask ourselves, do we have a moment? Sorry, do we have moment about Z? Let's do something simple first, okay? So this is rotation about Z, and we know that AY, right, for this case, right, AY And AX is going to what? Generate. Okay, it's going to generate. Hey, all of a sudden I cannot spell generate. About Z-axis. Okay, right? Do we have moment about point Y or about the Y-axis? Question again, do we have moment about Y? The answer is yes. Why? Because over here, do we have a perpendicular distance about Y? Yes or no? There is. So this and over here, AX will generate a moment about what? About the Y-axis also. Okay. So you guys think that's not difficult enough. If it's not difficult enough, the next thing we have to know, we have to consider what? We have to consider sandwich material. So with sandwich material, this expression will come out to be different now. So this is the formula that we have to use now. Are we clear? So it has every component you can see in the chapter of what? Bending. I'm just introducing to you what you're going to see in 3 weeks' time or 4 weeks' time. This is still simple. We only consider what? Bending moment. We totally throw what? Shear out of the window. There's actually some more what? Shear stress. But now let's consider what? Bending moment. Okay, or normal stress. Are we clear? You've seen the equation at the top before, yes or no? Dx over A plus by MYZ multiplied by IYY, MZ over IZZ multiplied by Y. Yes, seen it before. The one below is just what? For what? Sandwich material. Okay. I will provide you the first term in your formula sheet. Okay, I want you to a lot to remember. Fine. Okay. The next most difficult thing is the what? Analysis. You plug in the wrong numbers, good luck. Okay, you have to be really, really what? It gets worse later in this course. Okay, it gets worse. Okay, let's start from here then. Okay, so looking at the components that we have, so far, anyone, any questions so far? Anyone? Are we good? Okay, so we are here to determine the stresses, the maximum stress in material 1 and the maximum stress in material 2. Question for all of you, where failure will occur? Failure will occur there. Are we clear? Okay, failure will occur at the end when you resist what? When you don't allow motion. Yes, sir. Okay, there will be another line down here. So this is the longitudinal view. This is the longitudinal view. This is the cross section. So if I take a section down here, this is what you see. Can you look at the transformation? Okay. Anyone else? Any questions? Yes. Because bending moment is the highest at that point. That's the only reason. Because bending moment is what? Over here, you have an axial distance and 2 meters is the longest distance. That is where failure will occur. Okay, and always a fact. Okay, if you have a piece of ruler, don't memorize this. Okay, don't memorize this. Okay? You bend this really hard. Eventually, where will give way? This region will give way. Are we clear? Don't memorize this. Always bring a ruler. Okay, get stopped by a traffic police. Show your ruler. Are we clear? Okay. Why were you speeding? We're not looking at my speedometer. Okay. 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 Right. So from here, we know that we have a few components to do now. Okay. So first of all, we're going to determine. Okay. We are going to determine our AX and AY. Okay. We are going to determine our forces. So I'm going to take this diagram. I'll start on the next page. Why am I on this page now? Sorry, okay, my bad. Okay, so now